Hi, so in this video, I will run through with you this segment of the chapter on light, which is on total internal reflection. Before we start, I have curated three very interesting videos on this phenomenon of total internal reflection. Please view the three videos. I have also shared the link on Google Classroom. So you might want to watch these three videos first before I give you the details of this phenomenon. So total internal reflection is a very interesting phenomenon when a light ray by right is supposed to pass through a transparent medium, but in this case it doesn't. In fact, it gets reflected completely at the boundary. So this is very interesting because when you, let's say you fire a laser pointer through water, you expect the laser pointer or the laser light to actually pass through the water and also exit the water because water is transparent. But under certain specific conditions, the light ray doesn't pass through. In fact, it gets totally reflected, and hence we call this phenomenon total internal reflection. So the definition here for total internal reflection is the complete reflection of a light ray in an optically denser medium at the boundary with an optically less dense medium. There are some strict criteria for this phenomenon to happen, so you need to always check this criteria. So number one, the light ray must be traveling from an optically denser medium to an optically less dense medium. For example, from water into air or from glass into air. So this is the first very important criteria to check. Now, the second criteria is when the light ray is traveling from the optically denser medium into the optically less dense medium, the angle of incidence must be greater than something we call a critical angle. Later on, I will show you how to derive this critical angle value. So these are the two super important criteria to note and to check for before you predict whether the light ray will get refracted as it exits the optically denser medium, or will the light ray get totally reflected within the optically denser medium. Now, I mentioned about critical angle. So the definition of critical angle is defined as the angle of incidence in an optically denser medium for which the angle of refraction in the less dense medium is 90 degree. Now, you take a look at this diagram. This diagram shows light ray traveling in glass is a optically denser medium compared to outside, which is air. So at critical angle C, what happens is the light ray actually hits the glass surface, the glass boundary, and then it gets bent and move horizontally like what my pointer is showing. So if you look at this, you notice that the angle of refraction is here and it's 90 degree. So therefore, when the angle of refraction is 90 degree, we call this angle of incidence here the critical angle. If I increase the angle of incidence to be bigger than C, so if I increase this angle to be bigger, then what is going to happen is this refracted light ray will now be inside the glass, and therefore this is reflection, bouncing off, and we call this total internal reflection. Okay, so this is the how I unpack the meaning of critical angle. So over here, as you can see, the light ray goes at this and hits this boundary. The angle over here is pretty small. The angle of incidence is pretty small. So therefore, this angle of incidence should be smaller than the critical angle. So when this happens, the light ray will refract and pass through and refract at in air, just as per normal, like what refraction happens. And since light ray is going from a optically denser into optically less dense medium, the refracted ray when it exits should be bent away from the normal, like what the diagram shows here. So over here we don't see any total internal reflection. We see refraction. Light ray passes through and gets bent. We get also a very weak reflected ray, but this is not totally reflected. Okay, so over here, this is the example of a normal light ray passing through and undergoing refraction, exiting the glass. And over here is an example of a light ray hitting the boundary and having the refracted ray at 90-degree angle refraction, and we call this angle incidence critical angle. And lastly, if we increase this angle incidence to be more than critical angle, we will get a complete reflection, and this is the phenomenon which is called total internal reflection. So how do we define and how do we find this critical angle? We can derive this critical angle once we know the refractive index of the denser medium. So how do we do that? If you recall, this formula is Snell's law, and refractive index of a medium is equals to sine I over sine R. So therefore, I have taught you all before that I don't really like this formula of I and R. I'll rather call this sine I. This angle should be the angle of the angle that is in a less dense medium, and the bottom angle R here should be the angle in the more dense medium. So if you look at this scenario of critical angle shown over here, this sine I, my angle incidence, I should actually take 90-degree because this is the angle which is in the less dense medium, and the denominator R should actually be the angle of C, which is in the more dense medium. So if we do that, sine 90 divided by sine C equals to 1 over sine C, and this is how we get this the equation for you to calculate critical angle. It's a very simple equation. Do memorize it, and if you know the angle, if you know the refractive index of a medium, you can then calculate out what is the critical angle for that medium, and after that you can then decide whether will a light ray traveling in that medium itself, can it pass through and exit the material, or will it be totally reflected at the boundary back into the material. Alright, so now it's time to practice applying this equation. Please pause the video and practice applying this equation. I will release my solution now. Last chance to pause the video. Okay, here goes. So we are given that the refractive index is 1.52. Plug in n equals to 1.52 over here, so 1.52, and we just have to take the arc sine of the fraction, and I got 41.1 degrees. So in your worksheet, you will find a lot more examples on how to calculate critical angle, and also do remember how to determine when total internal reflection takes place. Remember the two criteria. So now, some other applications of total internal reflection. This slide shows glass prisms in binoculars, and as you can see here, when light enters in, we want the light to be totally reflected at this point, at this point, at this point, at this point. So these 4 points, and we do this by using specially constructed glass with a very particular value of refractive index, and we using geometry. When we construct the binoculars, we ensure that the angle incidence at this point, at the 4 points that I mentioned just now, is more than the critical angle of that glass. And when that happens, we can ensure that there is total internal reflection, and that is how we can reflect the light into our eye. This is a very common application of optical fiber, and you can actually see this happening if, let's say, you have this fiber at home. We commonly use it at home in our audio system when we connect the device to a speaker. Technology is using optical fiber, optical audio, which is clearer and has less distortion. So I found this photo of optical fiber that I thought demonstrates and shows you that total internal reflection is real. You can see the diagrams here, but I thought that this photo actually makes it real. So this person fires a green laser in, and you can see the path of the laser here, and this is the point where there is total internal reflection. The laser gets totally reflected out. You don't see that the laser ray actually comes out and gets reflected because everything is completely reflected over here. So what makes this possible is that for optical fiber, there's a core material. The core material is surrounded by a coating. So actually, it's a transparent piece of wire, but in fact, it's made of two different materials: a core and a coating. The coating actually has a slightly lower refractive index. So when the laser light travels within the core, it's actually travel in the optically denser medium, and when it tries to exit the core, which is optically denser, into an optically less dense medium, that's the first criteria for total internal reflection. And by adjusting the angle incidence of the laser within the core itself, you can create total internal reflection when the angle incidence is more than critical angle. So we use this kind of optical fibers, multiple optical fibers, in fact, to transmit a large amount of data, and we use this in cables that we put under the sea, and that is how we get internet, how we are able to access websites that's housed in different continents. So optical fiber is good because compared to normal copper wires, because the data transfer rate is a lot faster compared to copper wires. It's also faster compared to radio waves and microwaves, because we're talking about the speed of light, laser, moving within the medium itself. Like what I said just now, there's lesser signal loss when we use optical fiber, and optical fiber are lighter and cheaper compared to copper. Medical use, we also use optical fibers in endoscope, which is used to look inside our body. I hope you will never ever get to experience this, but let's say when the doctor wants to see what's happening in our stomach, so or they can insert this optical fiber, this endoscope, through our mouth to our throat and all the way into the stomach to see. And we optical fiber is good because it can be bent, so it can enter your body, and light can pass through, and at the end of the endoscope, the light can be transmitted and you can see what's happening. This process is actually very painful, and after when the endoscope is being pulled out, most often the person will have a sore throat. Okay, because the friction will just brush against your throat, and it's not a good experience. Okay. Okay, other use, keyhole surgery. So this is another use of laparoscopy. which is used in keyhole surgery. So what happens is in this kind of surgery, there's no large incision being made. It's just a keyhole surgery, meaning in simple words, we poke a hole and then we insert this tube in for us to see what's happening. And you can see this video. Usually there are two holes being poked. One for you to insert the camera, the laparoscope for to see what's happening, and the other hole is for the surgical instrument. So optical fibers are used in such applications because they are thin and light, and therefore you don't need to poke too big a hole. Very obvious advantage. And they are flexible, so they can be bent, and it can pass through your throat and things like this. Okay, on to smart home application. So a rain sensor is a very useful thing. I use it at home. When it rains, my blinds will automatically close, and this is basically how a rain sensor work. So we also use rain sensor in our cars, and in slightly newer cars there is auto wiper which activates when there is rain, and there must be a rain sensor in front of the car for this to work. So basically what happens here is there is a detector here, as you can see, and there's a LED here. So the LED will constantly fire a light ray out, which will gets reflected off the windshield into the detector. So when there is no rain, the LED is able to reflect completely, and then it will reach the detector. Once the detector receives the signal, we know that there is no rain. However, when it's raining, there is also reflection, but because of this raindrop here, it affects the reflection and the amount of light that reflects. So therefore, less infrared light will reach the optical sensor. Therefore, once the detector detects a lesser intensity of the light, then it will know that, hey, there's actually something on the windshield, which is the raindrop, and that's how we can activate the wiper to start turning. And with this, we have ended this segment on total internal reflection. We have covered a few examples and applications of TIR. The most crucial part is the two criteria for total internal reflection to happen. So number one, the light ray needs to be traveling from an optically denser medium and wanting to escape into an optically less dense medium. And number two, the angle of incidence must be more than the angle of must be more than the critical angle. So these are the two criteria before total internal reflection can happen. Lastly, there's an equation that you have learned, which is sine c equals to 1 over n, and that will allow you to calculate the critical angle for every medium when you have the refractive index of the medium. So now you are able to start practicing on the different types of questions for TIR. Please do so, and I will see you again in class.